All right, this is experiment number 2. And actually what we do, the lab usually follows the lecture class. So if we're going to be talking about free fall and weightlessness, we'll usually do that maybe the previous week, depends on how the schedule works out. But everybody's familiar with free fall. You jump off a building or you fall off a building and gravity pulls you down. Well, there's a fellow by the name of Felix Baumgartner, a couple of years, about 4 or 5 years ago, he got a money from a group called Red Bull. And they put him in a balloon, they sent him up over 20 miles into the atmosphere, over 100,000 feet. I think it was about 120,000 feet. And he jumped out. Now he had a spacesuit on, essentially a spacesuit, because at that altitude, first of all, the temperature can be very, very low, and you might, but also the air pressure is so low you probably would die. So on the way down, he essentially had very little air resistance. So his speed increased. He got up over around almost 600 miles per hour until he got in the lower part of the atmosphere, and then air resistance began to increase and gradually slowed him down. Slowed him down to about maybe 85 to 120 miles per hour.
Wow.
And at that speed, what he did was he was traveling at a constant speed because the air resistance pushing up on his body balanced his weight. The weight was down, the air resistance was up, and he had felt a free fall and was falling at a constant speed. And that constant speed is called the terminal velocity. The terminal velocity. All right. Now what I'm going to do now is read from the book, and we'll try the experiment. But I think it's really interesting to hear about Felix Baumgartner. Another guy by Captain Joe Kinzer did the same thing about 1960. And that was before the space program, and they wanted to see what would happen if he did that. And he did survive. I think he may have had some frostbite. Joe Kittinger, Kittinger. It was about 1960, and you all have cell phones, so you could look that up. Well, now going back to page 2 of the lab manual, it says poke 2 holes in opposite sides of a paper cup. Poke 2 holes in opposite sides of a paper cup. So here's a paper cup, which I bought at my wife's own expense. So she would leave some money for me to pay for this paper cup. And then what I did was I punched a hole in each side. Now you're intelligent people. I'm going to let this thing go and gravity pulls it down. Nothing dramatic about that. Now what happens if I put water in the cup, but I put my hands over the holes? Well, nothing's going to happen. But if I take my hand away, maybe hold it with the other side, and go like that, the water's going to come out of the cup and it's going to get over my pants. And everybody's going to laugh at me. So I don't want to do that. I'm going to do it from this side here. So now we're going to go over to the water. And we're going to give this a try. All right, my assistant. Now I have my hands over the hole, my fingers over the holes. Like that. And I take my fingers away from the holes. No surprise there. The reason the water came out was because what? Gravity pulled the water out of the cup. Now I'm going to try it again this time though. And you go like that, and you just let it go, and nothing comes out until it hits the sink. Then the water splatters all over the place. Okay? Do it again. My assistant is saying I should do this again, but I just damaged the cup, but I'll try it again. Try it again. Do the first part again. Second part again.
Yes. Good.
And it splattered and got on my pants.
Oh.
Okay, it happens. All right, good. All right, we can go back over there now. Thank you, assistant. By the way, my assistant's name is Peggy. She didn't want me to tell you that, but her name is Margaret. But her parents called her Peggy, so she's been Peggy to me 52 years, well, probably longer than that, probably 54, 55 years by this time. All right. So we just did that, and it says in the book, on page 2 again, refill the cup and drop the cup into the sink. Note the water flow from the cup. It doesn't flow out of the water. It doesn't flow out of the cup until it hits the sink. Now, actually, this is important in terms of something called relativity. If you're in an elevator and the cable snaps, you will fall, the elevator will fall, you will fall, and if you have a pen or a pencil next to you, what happens, that thing is just going to stay right next to you until you hit the ground. It's called relative motion between the two, okay? So what's to explain the difference between what happened? Well, in the first case, the cup was being held by my hand and gravity pulled the water out. In the second case, what happened was the cup fell, the water fell at the same time, so nothing happened until it hit the ground and the water splattered at that point, okay? Now what we need to do is go to the second part. This is called free fall and air resistance. Free fall and air resistance. By the way, I'm from Philadelphia. And one thing that happens is you never lose your dialect. All those years ago. By the way, if you have a calculator, you can figure out my age. I was 27 years old when I came here. I was 27 years old and I married the woman of my dreams. And that was 52 years and 8 months ago, and she still puts up with me. Let's put it that way. Okay. So some of you are probably married, so you can think about that. What I'm going to do is I'm going to take this piece of paper, and I'm going to take the book, and I'm going to drop them at the same time. Now, you're intelligent people. Which one's going to hit the ground first? The book. Why? Why does the book reach the ground first? They're both made of paper. They both have air resistance, but the air resistance of the paper is great because of the weight of the paper and the surface area of the paper, and so you slow down. So that's free fall, but it's not really free fall in this case because you do have the air resistance buoying up on the paper. Now if I crumple the paper though, like this, the paper doesn't gain any weight. And if I drop it at the same time, which one hit the ground first? About the same, all right? Now if I took this to the top of a tall building, I don't think it would be exactly the same, because there'd still be a difference because of the weight of the book. But here it's just about the same. So in that particular case is that when you crumple up the paper, air resistance is negligible. Air resistance goes down. Air resistance goes down. It's negligible. And so they will hit the ground about the same time. Now the third thing here, step 3, well, it already said that. So using the book and the piece of paper which strikes the floor first, explain why. All right. Step 4, cut the paper and make it slightly smaller than the surface of the book. Cut the paper and make it slightly smaller than the surface area of the book. So here's the paper, there's the book, like that, and now I've lost the page. You can laugh. Physics should be fun. It should be fun. All right. It says, please place the paper on top of the book and repeat step 1. So I'm going to do that now. Like that. And they go down together. Now, why did that happen? Why did that happen? Oh, what was the book doing on the way down? It was pushing the paper out of the way. I'm sorry, it was pushing the air out of the way. So the air could not really affect the piece of paper. And as a result, they're falling together. Like that. Now this is an interesting story. I always tell this story, by the way. It's about being in a race car, or maybe you're on I-95 and you're in your car and you want to save gas. So what you do, you get right behind a big truck. They're maybe going 70 miles an hour and you're going to get about maybe 2 feet behind the truck. And what's the truck going to do? The truck's going to push the air out of the way. And so you can actually save a little bit of gas that way. And my assistant's saying, you shouldn't do that. And if the police officer catches you, you're going to probably get a ticket for doing that, right? But that's something. Oh, what about the Indianapolis 500? Well, it's cars. What they do is exactly what I just said. They get right behind the car in front of them, and they may save just a couple of ounces of gas, but it may make a difference in the long run. Now, the last thing of this topic is suppose I put the paper under the book.
Oh.
What's going to happen? They get down together. Why? I have a very quizzical look on my face. Why? Is air affecting the paper? Yeah. Is air affecting the book? Yeah. But the book is pushing the paper down. And so the paper will end up landing first at the bottom. They get down together because that's air resistance. So in terms of free fall and air resistance, if air resistance is negligible, I'm from Philadelphia, remember that. It doesn't really affect things. And then, unfortunately, in physics class, we usually assume in our problems, solving problems, that the air resistance is negligible. And so it makes the problems easier to solve. Okay? Now the last thing here is called reaction time. And my assistant is telling me to speed up on this. And it's really very interesting. Well, I think it's interesting. What you do is you take a meter stick or a ruler. Well, you have two people to do this. And you go like this, hold it up, and let it go, and you want to catch the thing, but your partner will not tell you when they're going to drop it. You see how far down it goes. In that case, about 40 centimeters. And that would lead us to our next topic. Okay, it's called reaction time. And at the age of 19 years old, your reaction is so much better than it is when you get older. When you're 40 or 60 or 80 or whatever it may be. So in my case, when my children were small, they used to play a game called Pac-Man. And they always used to win, and they laughed at poor Daddy. Daddy could never win at Pac-Man. Their reaction time was always so much better than my reaction time. And that's enough for this particular section.
Bye-bye.
No? Go ahead.